Hello, we're here for the practice problems for Unit 7 with rotation. And this assignment here, it's a lot, because this unit does tend to be a lot. But what is nice is that a lot of what this unit has to offer is stuff that is really equivalent to some of the stuff we talked about before. So looking at some of the things like rotational kinematics is a big clue that you can handle these problems just like we did back in the units that they're attached to. So let's take a look at this first question and see how that kind of plays out. So we have a bicycle wheel that has an initial angular velocity of 1.5 radians per second. Angular velocity is measured in, we use the symbol omega to represent that. So we have initial omega of 1.50 rads per second. And just like in physics, when we, in kinematics, when we were looking at kinematic problems, we have V and V naught. This is our initial omega, so we'll make this omega naught. And then in A, it tells us if it has an angular acceleration, if its angular acceleration is constant and equal to 0.3 radians per second squared, what is the angular velocity at 2.5 seconds? So angular acceleration is alpha, and they're telling us that that is 0.3 radians per second squared. And they also tell us the time in this one is 2.5 seconds. So they then go on to ask us what is the omega, what is the angular speed at that point of time. So looking at our equations that we got guessed all in the last video, at the very end, I want to choose one that has the same stuff we have, and we're looking at the kinematics section. And kinematics will essentially be this section right here. And this equation right there has all the things that I have pulled out already, so that's the one I want to use. So in letter A, we have omega equals omega naught plus alpha t, which is exactly like the equation V equals V naught plus AT, back from kinematics. So if we plug in here, we get omega equals 1.5 plus 0.3 times 2.5. No algebra necessary. We plug it into a calculator and figure out that our answer is going to be 2.25 radians per second. So that is our letter A. Letter B then asks us through what angle has the wheel turned between t equals 0 and t equals 2.50 seconds. When it asks us what angle has it turned through, it's asking us for displacement. And the angular version of displacement is just simply theta. So taking a look at our equations, we have a couple different options, I think. But I think our best option will be this equation here, which is the same as this equation on the other hand side, that side. So we should have some kind of experience using an equation like this. So let's copy that equation in and see how that plays out. So we have theta equals theta naught plus omega naught t plus 1/2 alpha t squared, and plugging in. Theta naught is 0 because we're assuming we're starting from no angle. Omega naught is 1.5. Our t is 2.5 plus 1/2 0.3 times 2.5 squared. And this is already solved out for us, no algebra necessary, and we wind up getting an answer of theta equals 4.69 radians. And once again, if you feel like you want to convert that back into degrees, you're welcome to do so, but the radian answer will be sufficient. All right, let's move on to number 2. question, they talked to us about how CDs work. So a CD has a coded pattern that is a very short distance below the very bottom of the CD. These pits, these information things, they spiral outwards towards the rim of the disk, and the innermost radius is 25 millimeters. So we'll label that as R1. So R1 will be 25 millimeters, or if we convert that to meters, 0.25 meters. R2 is the maximum radius, and that is 58 millimeters. So we put that as 0.58 millimeters. As the disk spins inside a CD player, the track is scanned at a constant linear speed of 1.25 meters per second. Since it's a linear speed, that will be a V. So we have 1.25 meters per second. And then A, what is the angular speed of the CD when scanning the innermost part of the track? And then it asks us as well the outermost part, and also asks us for the outermost part. So we'll get omega 1 and omega 2 as a result of this. So in letter A, to figure this out, we're trying to translate from linear into angular. So what we're going to use is one of our translation relationships. Most notably, this guy right here, because we're trying to go from the linear version of a variable to the angular version. So let's copy this down. We have V equals R omega. Okay, and since V is constant, we don't have to worry about changing that. We'll plug this one in a while. And for the inner side of this CD, the radius is 0.025, and then we have the omega. So to solve for omega here, and we'll close omega 1 too, because it's going to match the radius. We'll just divide both sides by 0.025, and we wind up getting an answer of 50 radians per second, and that is equal to omega 1. On the other hand, when we're looking at the omega at the outer edge of the our CD, we go 1.25 again for the speed. R2 needs to be 0.058, and we have omega 2 here. So same idea, divide both sides by the radius, and here we get a angular speed of 21.55 radians per second. And it has to slow down out at this point because there's a larger circumference, and we have to make sure that the speed of the disk rotating through the reader remains constant or consistent. All right. Letter B. The maximum playing time of a CD is 74 minutes. What would be the length of the track on such a maximum duration CD if it were stretched and put in a line? Here, this one isn't terribly difficult to kind of think out once you kind of think about how this is actually playing out. So we know the velocity is still 1.25 meters per second. And if it plays for 74 minutes, we know how long this is going. And if we're looking at how long the track is, we're looking at an x value. Now, because of the units, we need to convert the 74 minutes into seconds. So let's do a quick calculation, 74 times 60, and we get a time of 4,440 seconds. The equation we need to use here is very simple. We just have x equals dt, because we have a constant speed. We don't have to worry about any accelerations or anything. So here we have x equals 1.25, and our t must be 4440. So multiplying that out, we get a x value of 5,550 meters. Just out of random trivia, that's about 3.5 miles of track in one CD, which is quite a lot. All right. In C, it asks us, where does C start? There it is. What is the average angular acceleration of the maximum duration CD during its 74-minute playtime? Take the direction of the rotation of the disk to be positive. All right, so in this situation, we're kind of going back into angular equations, but we're still talking about kinematics. So we know that omega 1 is 50 radians per second from letter A, and omega 2 has to be, and we'll kind of think this is omega naught, if that makes more sense. And omega 2 is 21.55 radians per second from letter A as well. We know our time is 4,440 seconds to the end of the track. And then all we need to do is just try and solve for the alpha. Looking at our equations again, we're given a lot of information about this first equation up here. So that's the one we should probably look at in order to solve for alpha. Plugging things in here, we have omega 2 essentially equals omega naught plus alpha t. And looking at our angular speeds, we can kind of tell this alpha should be negative because this thing should be slowing down. So if I plug things in here, we have 21.55 equals 50 plus alpha times 4,440. So if I subtract 50 from both sides, I get negative 28.45 equals 4,440 alpha. And dividing that 4,440 to both sides, we get an angular acceleration of negative 0.006 radians per second squared. So that acceleration is very slow, but it does need to happen in order to maintain the appropriate play speed for our CD player. All right. In the video below, we'll pick up with number 3. So just scroll down and take a look at that.